Before history had words, before cities rose and empires fell, we watched the sky. In the moon's silent rhythms and the sun's steady path, we glimpsed eternity and began to measure it. This is the ancient, wondrous story of how humanity became the keepers of time. In the dimness of prehistory, when humanity was young and the world vast and mysterious, we first looked up. Above us hung the infinite canvas of the night sky, punctuated by countless stars and the ever-changing face of the moon. Our ancestors didn't have words for what they saw, but they understood its significance, the repetition, the patterns. They were the first to recognize that time was not simply an endless stream, but a cycle that could be measured, predicted, and understood. In the flickering light of fires, early humans made the first marks to track the passing of time, not with pens on paper, but with ochre and charcoal on cave walls. Each mark, a notch, a dot, a line, represented a day, a night, a cycle of the moon. Imagine the first timekeepers, not scholars in towers or priests in temples, but hunters and gatherers who needed to know when animals would migrate, when plants would bear fruit, when the seasons would change. For them, time was not an abstract concept, but a matter of survival. In the caves of Lascaux, among the famous paintings of bison and horses, archaeologists discovered something even more profound. Sequences of dots and lines that match the phases of the moon. Dating back 15,000 years, these may be humanity's earliest attempts at creating a lunar calendar. The pattern was simple but revolutionary. The moon waxes and wanes in a predictable cycle of approximately 29.5 days. Our ancestors didn't need to understand the celestial mechanics. They simply needed to observe, to count, to remember. And so began humanity's long relationship with the moon. Our first clock. Our first calendar. This relationship would shape civilizations, guide farmers, dictate festivals, and eventually lead us to the complex timekeeping systems we use today. But the journey from those first scratches on cave walls to the digital calendars on our phones was neither simple nor straightforward. It was a path of ingenuity and error, of scientific breakthrough and cultural conflict, of compromise and correction. This is the story of how humanity learned to measure time. Long before the first cities rose from the plains of Mesopotamia, before the first hieroglyphs were carved into Egyptian tombs, the moon ruled our understanding of time. In the Indus Valley, where one of the world's earliest civilizations flourished around 3300 BCE, lunar cycles governed religious ceremonies and agricultural planning. The people who built the sophisticated cities of Harappa and Mohenjo-Daro watched the night sky carefully, marking the moon's journey from new to full and back again. In ancient Arabia, nomadic tribes navigated the harsh desert using the moon as their guide. The Arabic word for month, shahr, shares its root with shahara, meaning to become famous or to become apparent, just as the new crescent moon becomes apparent in the sky. The Islamic calendar, still in use today, is a purely lunar calendar with 12 months of 29 or 30 days each. It cycles through the seasons, completing a full cycle every 33 solar years. When it was established in the 7th century CE, it was built upon traditions that stretch back to the earliest days of human civilization. Across the world in India, the tradition of Karva Chauth exemplifies how deeply lunar calendars have embedded themselves in human culture. On the fourth day after the full moon in the Hindu lunar month of Kartik, married women fast from sunrise to moonrise for the safety and longevity of their husbands. They break their fast only after seeing the moon's reflection in water, a ritual that has been practiced for centuries and continues today. The lunar calendar provided humanity with its first reliable method of marking time beyond the immediate cycle of day and night. It allowed for planning, for anticipation, for memory. Agricultural societies could prepare for planting and harvesting. Religious communities could schedule their rituals and festivals. Traders could arrange meetings. But the lunar calendar had a fundamental flaw. A complete cycle of lunar phases takes approximately 29.5 days. 12 such cycles, a lunar year, amounts to about 354 days. But the Earth's journey around the Sun, the solar year that determines our seasons, takes approximately 365.25 days. For many cultures, this drift was acceptable. Religious observances are frequently subservient to the lunar calendar, cycling through the seasons. For example, the birth dates of many Hindu saints and deities are on different solar dates every year, while the month of Ramadan occurs 11 days earlier each solar year. But for agricultural societies dependent on seasonal planning, the lunar calendar alone was insufficient. This discrepancy of 11 days meant that a purely lunar calendar would drift through the seasons. Festivals meant to celebrate spring harvests would eventually occur in winter. Agricultural guidance based on lunar months would become increasingly unreliable. Humanity needed something more. The limitations of the pure lunar calendar became increasingly apparent as agricultural civilizations grew more complex. Farmers needed to know when to plant and harvest, tasks intimately tied to the solar year and its seasons. Yet the cultural and religious significance of the lunar cycle remained profound. The solution, a compromise, a fusion of lunar observation and solar awareness. The earliest lunar-solar calendars emerged in Mesopotamia, the cradle of civilization between the Tigris and Euphrates rivers. By the 3rd millennium BCE, the Sumerians were already using a calendar that tracked both lunar cycles and solar seasons. Their system was ingenious but imperfect. They followed 12 lunar months, but periodically inserted a 13th month, a practice called intercalation, to realign their calendar with the solar year. The decision of when to add this extra month was initially made by priests or kings based on observation of the stars and crops. In ancient Egypt, the flooding of the Nile, crucial for agriculture, coincided with the heliacal rising of Sirius, the brightest star in the night sky. This astronomical event occurred roughly every 365 days, prompting the Egyptians to develop one of the first solar calendars around 3100 BCE. They divided the year into 3 seasons of 4 months, each month having 30 days, with 5 additional days added at the end of the year. But it was the ancient Greeks who made one of the most significant breakthroughs in aligning lunar and solar time. In the 5th century BCE, the astronomer Meton of Athens observed that 19 solar years almost exactly equal 235 lunar months. This relationship, now known as the Metonic cycle, allowed for a reliable pattern of intercalation. 7 extra months added over 19 years would keep a lunisolar calendar aligned with both the moon's phases and the solar seasons. The discovery was so significant that, according to legend, the formula was inscribed in golden letters in Athens, giving rise to the term golden number in calendar calculations. The Jewish calendar, which dates back to approximately the 9th century BCE, incorporated this knowledge to create a lunisolar system that remains in use today. Their calendar ensures that festivals occur in their appropriate seasons while still beginning each month with a new moon. Half a world away, Chinese astronomers independently developed their own lunisolar calendar. By the time of the Han Dynasty, they had created a sophisticated system that used the winter solstice as a fixed point and incorporated intercalary months according to a 19-year cycle similar to Meton's. The Hindu astronomers of ancient India were already using a lunisolar calendar from as far back as 1000 BCE during the Saka era, which was further refined for hundreds of years by prominent Vedic astronomers. This incredibly complicated calendar system is called the Panchangam and is the basis for prayers, festivals, and astrology in Hinduism. These early attempts at reconciling lunar and solar time were remarkable achievements of ancient science, yet they still required constant adjustment and maintenance by dedicated astronomers and priests. The perfect calendar, one that would accurately reflect astronomical reality while remaining simple enough for everyday use, remained elusive. The search would continue. As Rome rose to dominate the Mediterranean world, so too did a new approach to timekeeping. The pragmatic Romans, with their genius for administration and standardization, would transform how humanity measured the year. The early Roman calendar was a lunisolar system with 10 months, beginning in March. This unusual arrangement left winter as an uncounted period, a reflection perhaps of its agricultural insignificance. The calendar year contained only 304 days, with periodic intercalations to realign with the solar year. It was, to put it simply, a mess. By the time Julius Caesar rose to power in the 1st century BCE, the Roman calendar had fallen out of alignment with the seasons by several months. Political manipulation of the calendar for electoral advantage had only worsened the situation. In 46 BCE, after consulting with the Alexandrian astronomer Sosigenes, Caesar implemented what came to be known as the Julian calendar, a solar calendar of 365 days with a leap year every 4 years. This reform created the Year of Confusion, a transitional year that lasted 445 days to realign the calendar with the astronomical reality. Caesar's reform was revolutionary. By essentially abandoning the lunar connection, the Julian calendar achieved a simplicity and accuracy that made it practical for the vast Roman Empire. Each month was given a fixed number of days, creating the familiar pattern we still use. 31 days for January, March, May, July, August, October, and December. 30 days for April, June, September, and November, and 28 or 29 days for February. The Julian calendar spread with Roman power and influence. Even after the empire's fall, its calendar endured through the influence of the Christian Church, which adopted it for calculating religious observances. But even Caesar's astronomers couldn't overcome a small but significant error in their calculations. The solar year is not exactly 365.25 days. It's approximately 365.2422 days. This difference, about 11 minutes per year, would accumulate over the centuries, causing the calendar to drift from the astronomical reality it was meant to track. By the 16th century, this drift had amounted to 10 days. The vernal equinox, which should have fallen on March 21st, according to church calculations for determining the date of Easter, was actually occurring on March 11th. Something had to be done. In the late 16th century, the accumulated error in the Julian calendar had become impossible to ignore. For the Catholic Church, this was not merely an academic concern, but a theological one. Easter, the most important feast in the Christian calendar, was supposed to follow the first full moon after the spring equinox. With the calendar's drift, this sacred timing was in jeopardy. Pope Gregory XIII convened a commission of astronomers and mathematicians to address the problem. Their solution was both elegant and pragmatic. The Gregorian reform, implemented in 1582, made two critical changes to the Julian system. First, it removed 10 days from the calendar to realign it with astronomical reality. October 4th, 1582, was followed by October 15th, 1582. Second, it refined the leap year rule. Under the Julian calendar, every fourth year was a leap year. The Gregorian reform maintained this pattern, but with an exception. Century years ending in a double zero would only be leap years if they were divisible by 400. Thus, the years 1600 and 2000 would be leap years, but 1700, 1800, and 1900 would not. This subtle adjustment, skipping 3 leap years every 400 years, reduced the calendar's error to approximately 1 day in 3,300 years. The Gregorian calendar represented the triumph of astronomical accuracy over tradition, yet its adoption was far from universal or immediate. Protestant countries viewed it with suspicion as a Catholic imposition. Orthodox Christian nations clung to the Julian system as part of their distinct tradition. Great Britain and its colonies, including what would become the United States, did not adopt the Gregorian calendar until 1752, by which time they needed to remove 11 days. Legend has it that riots erupted with people demanding, "Give us back our 11 days." Russia held out even longer, maintaining the Julian calendar until after the Russian Revolution in 1917. When the Soviet government finally made the switch in February 1918, the difference had grown to 13 days. The Gregorian calendar, with its months of varied lengths, its subtle leap year rule, and its complete detachment from lunar cycles, might seem arbitrary to modern observers, yet it represents one of humanity's most successful attempts to reconcile the messy realities of astronomical time with our need for a standardized, predictable system. Today, the Gregorian calendar serves as the international standard for civil use. Its months no longer track the moon's phases. Its structure bears the scars of political compromises and historical accidents. Yet, in its function, providing a stable, accurate framework for marking time across years, decades, and centuries, it has proven remarkably effective. But the story of timekeeping doesn't end there. The Gregorian reform solved the problem of the calendar year, but humanity still faced challenges in standardizing time across hours, minutes, and eventually, seconds. As humanity entered the industrial age, the need for precise timekeeping extended beyond the calendar to encompass hours, minutes, and seconds. The mechanical clock, which had been evolving since medieval times, revolutionized how people experienced daily time. The introduction of railways demanded standardization of time across regions. Before the 19th century, each town kept its own local time, based on the sun's position, but with trains connecting distant locations, this system became impractical. The concept of standard time zones emerged, with the world eventually divided into 24 zones, each ideally 1 hour apart. In 1884, at the International Meridian Conference in Washington, D.C., the Greenwich Meridian was established as the prime meridian, the line of longitude from which all others would be measured. Greenwich Mean Time, GMT, became the standard against which all other time zones were defined. The 20th century brought further refinements. In 1967, the definition of a second was changed from a fraction of a day to a precise count of radiation cycles in a cesium-133 atom. This atomic second became the basis for Coordinated Universal Time, UTC, which replaced GMT as the world's time standard. To everyone's surprise, the atomic clock's precision revealed that Earth's rotation isn't perfectly consistent. It gradually slows down due to tidal forces. To accommodate this, leap seconds are occasionally added to UTC to keep it aligned with astronomical time. It seems the closer we get to solving time, the more complex it becomes. When digital computers emerged in the mid-20th century, they needed their own timekeeping systems. Unix time, which counts seconds elapsed since January 1st, 1970, became a standard in computing. The Network Time Protocol allowed computers to synchronize their clocks across the internet. For everyday users, digital calendars transformed personal time management. No longer constrained by paper, these systems could automatically adjust for time zones, send reminders, and coordinate schedules across continents. Today, our devices synchronize with atomic clocks through the internet. The smartphone in your pocket keeps time with an accuracy that would have astonished the astronomers who advised Pope Gregory. Your calendar app can instantly convert between time zones, calculate the days between dates, or remind you of an appointment precisely when needed. Yet beneath this digital facade lies the same Gregorian calendar structure established over 4 centuries ago. 12 months of varying lengths, with a leap year every 4 years, mostly. Our modern convenience rests on thousands of years of human observation, calculation, and compromise. From the cave paintings of Lascaux to the atomic clocks of today, humanity's quest to measure time reflects something profound about our species. We are creatures who seek patterns, who plan for the future, who remember the past. The calendar, in all its forms, represents our attempt to impose order on the chaotic flow of existence. Our calendars have never been perfect reflections of astronomical reality. They are compromises between accuracy and usability, between scientific precision and cultural tradition. Despite their imperfections, calendars have served as the framework for countless human experiences, marking our birthdays, vacations, festivals, harvests, and holidays. In a very real sense, calendars don't just measure time, they create it. They transform the continuous flow of days into meaningful units. Weeks, months, years, decades, centuries. Perhaps what's most remarkable about our calendars is not their accuracy, but their universality. In our divided world, the Gregorian calendar stands as one of the few truly global standards. When people across continents and cultures refer to January 1st, they mean the same moment in time, a shared reference point in our collective human journey. But the fundamental challenge remains the same: how to reconcile the messy astronomical realities of our planet's movements with our human need for order and predictability. The Earth doesn't orbit the Sun in a neat number of days. The Moon doesn't cycle through its phases in a whole number of days. The Earth's rotation is gradually slowing. And as we continue to explore space and perhaps one day establish communities on other worlds, new calendars will be needed. A Martian year lasts 687 Earth days. Its day is slightly longer than Earth's. How will humans mark time there? What new compromises will be required? The calendar's story is not finished. Like time itself, it continues to evolve, shaped by the never-ending dance of the Earth, Moon and Sun, and by the human desire to understand, to predict, to remember. From those first scratches on cave walls to the synchronized digital displays on billions of devices worldwide, we remain, as we have always been, the keepers of time.